All right, here we go. Looking at chapter 2, or excuse me, chapter 4, a little bit further. We're going to be identifying functions and finding the domain and range of relations and functions. We're going to do this in two different parts. We're not going to be identifying functions in this part. We're just going to be concentrating on domain and range and how that, how to maybe represent these functions. Okay, so here we go. So we did talk a little bit about functions already with graphs, and we showed how you could make a relationship between two different things, like how far you've gone and your speed, and how that affects your graph and how that looks as a graph. But there are other ways to represent functions. One way is with ordered pairs. This is called set notation. Set notation, or what they call a relation. But it's set notation. So they give you the situation. I'll let you read it, so you can pause it if you want and read it. And it gives you, so again, I encourage you pause it, read the situation, and I'm going to keep talking. So it gives you this relationship about this track meet, and the way they represent the relationship, the way they represent this this system, is with set notation. And set notation is right here. And we use these little squiggly brackets on either side to show that it's a set. It's just another form of a parenthesis, but it distinguishes it from a regular parenthesis that we use for our ordered pairs and this other parenthesis that we're going to use for our set notation. And so this set says that we have first place gets 5 points, second place gets 3 points, third place gets 2 points, etc., and fourth place gets 1 point. This would be a lot like if you were looking at a GPA, a grading scale. A gets 5 points, B gets 3 points, C gets 2 points, and D gets 1 point, F would get nothing because you failed. And so we've got our system of how we assign points to a certain place value. So that's set notation. We're also going to be looking at tables, graphs, and what are called mapping diagrams. Now, mapping diagrams are a really nice visual way to show a relationship between things, and we'll use that to help us determine if something is a function as well. So we're going to look at some mapping diagrams. Here we go. So part of your assignment, or most of your assignment, will look like this. We're going to express this relationship, this set right here of ordered pairs, as a table, as a graph, and as a mapping diagram. So we're going to be making these. The table, which is the first one on our left here, we have our ordered pairs x, y, and of course x, y. So we've got our three different ordered pairs. So x, y, x, y, x, y. Oh, wasn't so bad. And again, the table is just telling us input, what's going in, and output, what is coming out. So 2 goes in, 3 comes out, 4 goes in, 7 comes out, 6 goes in, 8 goes out. And that's all we know. We have no idea what this is talking about, if it's talking about people or pizzas or electrons or I don't know. It's X's and Y's. That's all we know at this point. It's some kind of a relationship. Now we're going to graph that, those ordered pairs. So we've got 2, 4, and 6 are our X values. So on my X-axis, remember we've got our X-axis, our Y-axis, we've got 0, 2, 4, 6, and you could keep going, but that's all we really need. I've got a nice constant pattern there. My Y's go 3, 7, 8. Now I can't just go 3, 7, 8. That's not a constant pattern, so I might just have to go by ones. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8, there's 7, 6, 5, 4, here's 3. So I'm only going to label the ones I need because I'm lazy, but they are all there. And so all those dashes are in there. What the heck, I'll put them in. Why not? 4, 5, there we go. And now I'm going to plot those points. So 2, 3, 2 goes in, 3 comes out. 4, 7, 4 goes in, 7 comes out. And 6, 8. So 6 goes in, 8 goes out. My graph only needs to be as big as my points fit. As long as the points all fit, the graph is fine. Most of your graphs will be this L shape, just quadrant 1. However, you might have some in quadrant 2 or quadrant 3. So you may need to make your graph more of a full T. And so when I say that, I mean you may have to extend it down and extend it over. But But for this particular one, I only needed quadrant 1 because they're all positive. Now the mapping diagram. This is one that you have not seen before. Mapping diagrams give us our input. So again, here's the in, here's the out. So a lot like a table. Can't get the T, but that's all right. So my input, my x's, 2, 4, and 6. And my output, 3, 7, and 8. And how it differs, how it's different than a table, is that we're going to show by drawing some arrows where once 2 goes in, where it goes. So 2 goes to 3. 2, 3. 4 goes to 7. 4, 7. 6 goes to 8. 6, 8. So we draw those arrows. And again, part of you is probably thinking, well, that was pointless. For this particular set, it may have been a little bit because they're already right next to each other. The table shows that just fine. But we'll see how that works in other situations. The other thing I want to point out is with the graph here. You'll notice with the graph I did not connect the dots because we don't know if 2.5 is part of the set. If it's talking about people, then you could not have 2.5 in there. That wouldn't work. Even though you can have 4 or 2.4 children is the average, you can't have 0.4 children. And so that might not work. It might work. We don't know. It could be talking about pizzas, where you might be able to eat 2.5 pizzas. But we don't know. And so at this point, we cannot connect the dots. All we know for sure is that these 3 points do work in this set. That's all we know. So we're not going to connect the dots. So pause it, try it on your own. Try the same type of thing. Make a table, a graph, and a mapping diagram. Again, pause it, give this a try. I'm going to assume you paused it. I'm going to assume you tried to put these in on your own. So I'm going to do it a little bit quicker then. So the table, my input, 1, 2, 3. My output, 3, 4, 5. Okay, I'm going to make a table, 1, 2, 3. And we'll go. We'll just go 1, 2, 3, 4, 5 again. And 1, 2, 3. Okay. And I'm going to plot my points. So I've got 1, 3. I've got 2, 4, and 3, 5. And again, I'm not going to connect the dots because I don't know for sure if 1.5 will work. And I'm going to make my mapping. 1, 2, 3. 3, 4, 5, and connect the dots. Or excuse me, not connect the dots, sorry. Draw arrows. 1 goes to 3, 2 goes to 4, 3 goes to 5. Check your work, fix it if you need to. We're going to look at another example. Domain and range. Okay, so domain and range, a little bit harder. Not a little bit harder, a little bit more in depth. We'll say it that way. Domain and range is looking at those inputs and the outputs. The domain is what's going in. So it's the X values. It's the input. The range is what's going out. It's the outputs. It's the Y values. So for the track meet, we'll go back here. The track meet, here it is. We had this set of ordered pairs where 1 went in, 5 went out. 2 went in, 3 went out. 3 went in, 2 went out, 4 went in, 1 went out. The domain is that input. It's what are the different possible things we can talk about. We can talk about first place, second place, third place, and fourth place. We don't have a fifth place in this set. Only first, second, third, and fourth. And so the domain is all those X values, all the things that could go in. We can only talk about first place, second place, third place, and fourth place. We don't have a fifth place in our set. And then once we have those domain values, once we know what we can talk about, we have the things that can come out, the outputs. We can have a 5, a 3, a 2, or a 1 come out. You can only get 5 points, 3 points, 2 points, or 1 point. You'll notice you can't get 4 points. 5, 3, 2, or 1 are the only options. And so our range, 5 for first place, 3 for second place, 2 for third place, 1 for fourth place. No 4. Doesn't go 1, 2, 3, 4, 5. Just goes 1, 2, 3, 5. So our range is the outputs. It's what can come out. It's the Y values. So that's the range. And the inputs, or the domain, is what can go in. It's the x values. I'm gonna skip that. I'm gonna go here first, and then we'll come back. So we've got our table. We want to give the domain and the range of the relationship of the table. So I've got a domain, and I've got a range. The domain, that's not an O, sorry, that's a D. The domain is all the things that can go in. So that's my x values here. This is the input. So 1 can go in, 4 can go in, or 8 can go in. So in the domain, I'm going to draw my set. 1 can go in, 8 can go in, and, 1 can go in, 4 can go in. Apologize. 1 can go in, 4 can go in, and 8 can go in. So there's my bracket. So there's my domain. 1, 4, and 8 are all the input values. For the range, the output values. So I've got 1, 4, or 1 can come out, and we're going to see what happens here. So 1 can come out, 4 can come out. Now 1 comes out again, but we've already got 1. 1 is listed already. This is, again, just telling you what's possible. What are the possible outcomes? Well, 1 is a possible outcome because 1 happens right here, and 1 is an outcome. It happens right here, but it's just that number, 1. And so we don't list it twice. We only list it once because it's one option. 4 could come out or 1 can come out. There are only 2 things that could come out, a 1 or a 4. So we only list the things that can come out. Look at this one. Now, this one, we've got a graph. This is a little bit different, and it's connected. The points are connected. So if we look here, we're giving the domain and range again. So, okay, domain, I use a different color, range. So the domain, what can go in? So remember the domain is the x values. So the x values. So if we look at my graph, 0. If I put 0 in, I get nothing in the y column. There is no out for the 1. For 0. If I put 1 in, I get a result. 1 goes in, 4 comes out. So 1 goes in, 4 comes out, which means that 1 could be part of my solution, or it could be part of my domain. Let's look at 2. 2 goes in, and it looks like maybe 3 3/4 comes out. 3 goes in, 2.5 or 3.5 comes out. 4 goes in, 3 1/4 comes out. 5 goes in, 3 comes out. 6 goes in, nothing. Nothing comes out when I put 6 in. So it looks like it goes from 1 all the way to 5. But that's it. It doesn't go anywhere past 5. And so when I put that in, 1 is the lowest value of the x's. For those x's, 1 is the lowest value, and 5 is the highest value. 2 works, 3 works, 4 works, etc. However, I'm getting long here. However, everything else in between works too. 1.5 works, 2.5 works, 2 1/4 works, 2.1 works, 1.0111001 works. We have all these decimal points in between. All these x values work between 1 and 5. They all get a result. They all come up and hit the graph at some point. So the way we show that is by saying that x could be between 1 and 5. Hey, we've done these. It's a compound inequality, and we are going to include 1 and 5. This is an inclusive club. We are including 1 and 5 in this because we have closed-in circles. And closed-in circles means we're going to include them, and everything in between. Let's look at our range. Okay, so range values. Range values, we've got, there we go. If I look here, 1 goes, well, if we kind of turn our heads a little bit, 1 does not cross the graph. 2, nope, nothing there. 3, yep, there we go. It hits it right at 3 there. 4, yep, gets to 4. 5, no. So that means that our range values, our y values, remember we're looking at the y values now for the range, the y values could be 3 or 4, or again, anything in between. 3.5 comes out and hits the graph. 3 3/4 comes out. So they hit the graph in a lot of different places and everywhere in between. So we get this long range of range values in between 3 and 4. All those little points in between would come out and give us a result. So we're going to say that y, not x, because again we're looking at y here, y could be between 3 and 4 on that graph. And again, we are inclusive. We're going to include 3 and 4 because it's closed circles. And we have our domain and our range. Any x value between 1 and 5 will work in this relationship. And when we put in anything between 1 and 5, including 1 and 5, we will get a result between 3 and 4. And that's how we would say, that's how we would define our range and domain for this function. Last one. There we go, mapping. Okay, we got lots of different arrows here. Again, this is where the arrow notation kind of helps and actually is meaningful. So if I look at my my set here, 6 goes to -1, 5 goes to 0, 2 goes to -4, and 1 goes to 0. So if you were going to make a graph or a table of this, it would go 6, -1. It would go 5, 0. It would go 2, -4. See, -4. And it would go 1, 0. Right, did I miss any? 1, 2, 3, 4. Oh, yes. It would go 1, 0. And you'll notice that 0 pops up twice. So that would be the table. I'll leave that up there. That isn't actually part of the problem, but I'm going to leave that up there just so you can see it. So that would be the table. Okay. The domain and range. So the domain, there we go. Domain is all the x values. It's all the things that could go in. So we would have 1, 2, we're going to go in order here, 1, 2, 5, and 6. Then you'll notice that 3 and 4 are not part of that domain because they're not listed. The y values, again, in the table, you'll notice 0 comes up twice, but we only need to list it once. So the range values would be -4, -1, and 0. So, oops, excuse me. Go in order here. -4, -1, and 0 would be our range. And that would be it. So try these questions below. Give them a shot. Check your answers, because remember the answers are going to pop up at the end once you've submitted, and then we'll work on the assignment in class.